Sounds like a good shadow.
No. Do you know where it is? You guys really can hide it? I don't know where my smiley face went. Yeah, like the one that was normally on that side. I told Connor he was going to start hiding it as like a fun little game. But then
I think this game's going too far.
I know. Connor says it wasn't him, so.
The hunter has become the hunter.
I'll crawl underneath the desk.
That was going to be the game, was like he would hide it and then he would like find it, you know. But I really have no idea what. So,
I print a new one, do I get a smart?
well, that was the rule I told him. Yeah, he brings in a bunch of stuff. Okay, so last time we learned in our quiz about rate laws and rates. Okay, a rate, once again, is just the speed of a chemical reaction. Once again, think of it just like a car is miles per hour, reactions are in molarity per second. What we learned is last time, given experimental data, you can calculate a rate law, which tells you how each piece affects the speed. In this unit, I want you to keep in your mind, we're going to learn 3 other methods for calculating rate laws. Or I guess 2 other ones. So we've learned one already. It all is going to get us to that same goal of rate equals K, brackets, and orders. But there's different methods depending on kind of the data you gather or the type of experiment that we're forming. Okay? Now, we talked about last time that in order for a reaction to happen, they have to collide. If they don't collide, then there's no chance of it ever happening. But, make a little side note here, just because they collide doesn't mean they react. And when it comes down to probability, it's actually very, very low. Most collisions are unsuccessful. Most of the time, they collide and bounce, and they don't actually change. There's some things that have to be there to actually make it happen. Now, the first types of reactions we're going to talk about are known as elementary reactions. An elementary reaction is a reaction that literally only takes one right collision. This is an example of an elementary reaction. Now, once again, everything has to be correct, but if it is, it just takes one collision to make it happen. The one collision is the NO and the O3 are colliding, and it has to hit in such a way, right, that this hits with this, so it can break it off the other half. Okay? But that's what an elementary reaction is. An elementary reaction is a reaction that requires a single collision. Now, we have 3 types of elementary reactions. We have unimolecular, bimolecular, and termolecular. A unimolecular is a reaction that is only actually a single molecule involved. Can anyone think of, when we've classified our different types of reactions, of what type of reaction that we've talked about would be considered unimolecular?
It would be like a decomposition reaction.
Perfect, Josh. How does my face for that? Yep. Unimolecular are decomposition because it's just one thing breaking apart. Okay? Bimolecular means 2 things are colliding. Termolecular means 3 things are colliding. Now, I have a weird visual for you, but you should be used to that by now, right? So, okay, if you've seen Harry Potter, if not, you still visualize. But in first Harry Potter, he goes into a room and there's a bunch of flying keys. Okay? If you haven't seen, just imagine a bunch of flying keys, okay? Now, also add to the room a bunch of flying padlocks. Okay? This is a dangerous room to be in. Okay? A chemical reaction doesn't work just because a key hits a padlock. What has to happen? It has to be the right key in the right padlock in the right way. Right? If the padlock's like this, you know, it's like they can hit a lot of ways and just bounce off each other. So, a termolecular reaction is extremely rare. A termolecular reaction would be like 2 keys and 1 padlock. And it all clicks at once. Not this key, then the other key, but literally all at once.
So what if it were a double-sided padlock?
No, it is. So it's a double-sided padlock. But it's like, imagine them flying through the air. The probability of both keys going in the padlock at the exact same time in the right exact place.
And then turn.
Okay, like just make a note, these are very rare. So if the question is this a term molecular reaction? The answer most of the time is no. It's not doing that because it's just so rare for that to happen. Done?
Yeah.
Oh, you're awesome. Yeah, you want to tell Hunter with the lab. Okay. All right, so these are some examples right here of elementary reactions. Okay? Now, by knowing that something is an elementary step, meaning it only takes one collision to happen, you can write the rate law directly from the stoichiometry of the equation. But the only way we can do that is because we know it's elementary. Now, the way you're going to know that it's an elementary step is the problem will tell you. Because this is something that's determined experimentally outside of what we can do in this class. Okay? So if a problem says, hey, this is an elementary process or an elementary step, the rate law literally is the stoichiometry of the equation. So for this one, the rate law is just A. For this one, it would be A squared, so on and so forth. Questions on any of those patterns?
There's no black markers in here, doesn't matter what color.
It does need black, so just don't put them out. I'll find some more black ones.
Okay. And then, do you know who the rulers are?
First set of drawers, second one.
Okay.
I think, maybe third. Questions on the patterns of how that works? So how we get from here to there. Notice something else. Why is this one still considered bimolecular? Yeah, it doesn't matter that it's the same thing, right? There's still two of them. Yeah, Jordan.
Would diatomic ones be considered bimolecular?
Ooh, you tell me. Are diatomics two molecules?
No.
Good. So yep, it'd just be one. But great question. Yeah, so the subscripts don't actually matter here. So great question though. Other questions on the pattern? Okay, let's try for some smiley faces. With your table buddy, fill in this table. Ready, set, go. By the way, the rates on this problem should not have A's and B's because there are no A's and B's in this problem. Hey, when you're done, put your pencil down so I know you're ready to check it. Tell me this first one. Up here. And then set your pencil down when you're done. Hey, everybody, it's Ethan's birthday today. Well, we're not dying here. Is that how we
Pencils down. I'll start to see you.
You are correct. It is not working. Okay, but we'll just answer it. Okay, I must have missed something when I typed it up. Probably a balancing or something.
Is that the bottom of this?
Or maybe it's supposed to be.
Chemistry has broken something.
Oh, did you find the broken equation? Oh my
Discovered something new in chemistry. Math can't be destroyed.
Okay, wave your arms if you need another minute. Or if you're ready to check. Okay, 30 more seconds. And then we'll check it.
Sure, why not? No. It's NOC with either. That's what it looks like now. Okay, that one's lower. So.
Maybe it's supposed to be like a liquid. I don't know.
Oh yeah.
This is what happens when you make a note packet way too late at night.
Yeah.
Good? Okay, eyes up front. Okay, alright, let's go ahead and check this. If you got them wrong, then please ask so we can make sure we understand it. Okay? Alright, so first off, let's do the molecularity. So this is one reactant, so you should have that it's unimolecular. This one has two of those and one of those, so it's termolecular. This one should be bimolecular, and that one should be bimolecular. Woo! So you can have a smiley face for each. Question, right?
Here's around the class. If it has two products, that change.
Good question. Look at the table above. Did the products ever affect what it was?
No, it just says products.
No. So it doesn't matter how many products we have, what the products are doing when we're looking at molecularity or even rate laws. So good question though. Okay, rate laws. Now keep in mind the structure of a rate law. The problem says what is the rate law? You should write out this form. Okay, you should write rate equals little k, and you have to have the little k because that's part of it, and don't make it capital because that's something totally different. Okay, and then for this one, the reactant is N2O4. Okay, now for this case, if you didn't write rate equals, that's fine, but just recognize like that it's a whole expression that you should have. Okay, all right, good on that one?
Yeah.
All right, this one you should have rate equals k, and then NO should be squared. And then O2. Next one, rate equals K, and then CO and NO2. And last one, you should have NOCl squared. Questions on any of those? You can have a smiley face for each correct rate law. Yeah, so that's up for 8 smileys. Questions on that? Okay, now, I have a question for you. Ready? With your table buddy, I want you to discuss this before we go on to the next topic to make sure we understand something, okay? Why were we allowed, so you're going to turn to your table buddy and answer this verbally, okay? Why are we allowed to write the rate law from just the equation on these? Because last class period we had to use all this data to find the rate law. So what's different about these from last time? Turn to your table buddy and tell them what you think. Like, what do you mean do stuff for you?
Like in stats, like different things. Like we do unipolarity,
Oh, like type an equation in and like tell it. But I wouldn't doubt it. Oh, then I might lose my job, right? They wouldn't be a teacher.
They just have the
Okay. Someone by raise their hand, who's willing to share their thoughts. That was a weird way to say that, but you know what I meant. Okay, everyone please listen to Ben.
So our thoughts.
Not you, not
You can listen if you want. So our thoughts were that these are elementary steps, not the steps that we were doing last time,
Yes.
and that's why it's different.
This is the key word. Don't get carried away. This is a fairly easy thing, right? And what happens is because it's easy, some students default to it and they just do this every time.
What were we doing
And does that work every time?
Before is like the quiz. We had all the data and we had to compare this changed and that didn't change and so on and so forth, right? For example, that's a good point, Macy. So like on the quiz, the equation on the quiz was A plus B turns into C. If you just wrote the rate from that, you would be like, oh, okay, well, the rate is K A B, which was not the rate at all. The rate was K A squared, okay? So if a problem doesn't tell you that it's elementary, then you have to use some other form to find the rate law. Got it? Okay, next topic. Skipping that. Okay, so going back to the idea of our keys and our padlocks flying through the air, that refers to the fact that you have to have proper orientation of collision. Okay, the molecules can't just collide, they have to collide in the right spot. If they don't collide in the right spot, then they simply just bounce off each other.
So when you have reactions though, like what we did a couple of days ago, why was it such great if you're saying like, oh, the chance of the chance of collision and getting it
It's really low.
Is it just because you have so many molecules?
Yes. Yeah, it's just the perception difference for us to how many molecules are actually in that flask, right? But if you actually compared how many collisions were effective versus how many weren't, there's way more. But for us, that's why some reactions appear to like, oh yeah, but we don't see all the ones that don't work. So great point though. So keep that in mind. It's all about we need to form a new bond and it needs to form at the right spot. In this case, Cl is trying to bond with that Cl. So if the Cl hits somewhere else, bounce off each other and they go on their way, right? Yeah, Eli.
Does polarity have to do with this?
Being in the right spot so that it's
It could, depending on the reaction, it could maybe help with it. Maybe. I don't know. I can't answer that for sure. Because then they could have a little bit of a magnetic like pole, right, to help them. I don't know like the definite answer, but my logic would say like it could help in certain cases if they were charged certain ways. So like in this case it probably wouldn't because this doesn't have a charge. Because technically it's like, and that would have a charge. But yeah, but great question or comment on that.
I'm just looking for food dye.
Go on the other side of the big table. Very far side on one of those shelves is a bunch of box of food coloring.
Chlorine dye.
Yeah, so this is only showing one part of a collision. But yes, great observation. It doesn't actually exist that way. Now, here's the other thing. They can hit the right way, and it still not work if they don't have enough energy to actually break those bonds. So we have two pieces. You have to have orientation and energy. So the energy factor was determined by this Swedish chemist named, I don't know how to say his first name, but Arrhenius is his last name. Okay? And he figured out that there's a minimum energy that's required in order for them to react. The minimum energy, this right here, is known as the activation energy.
Is that gonna have to do like our close?
kinda, every reaction has an activation energy. A minimum amount of energy it takes for it to go. The higher the activation energy, then the more energy it takes, and sometimes the harder that reaction takes to go. Things that have a very low activation energy don't take much. For example, most combustions have a very low activation energy. To make something burn that goes through combustion, it just takes a small spark, right? That's literally what your car does when you turn your key, is it sparks the start of the combustion, and then it will just continue to go. Other reactions need a lot of energy to actually make them happen. Now, once again, if they don't have enough energy, they just bounce off each other and go on their way. So we have to hit in the right way and with enough energy. Now, let's focus on this graph here on the left for a second, because it should look familiar. Okay? For a smiley face, don't say it out loud, but which of these colors on this graph, from what we've learned before, would represent a molecule at the highest temperature? So in your head, pick a color. Which color represents a molecule with a really high temperature, or the highest of them all? Everyone have an answer? Chance to bless you. Okay, so this purple's gonna be number 1, light blue's number 2, yellow's 3, dark blue's 4. Show me what you think on your hand. So which one would have the highest energy? Okay, 5's not a choice. Okay, good. You guys remembered. 4. So why does this one have the highest temperature? Good. So the speed is the highest, the higher the temperature is. Good. Have a smiley face if you got that right. Woo! Okay. Now let's remind ourselves, though, why does the graph get flat? Like, it's getting faster. What's with the, flatness of it? What was that?
The same total number of molecules, so they have to be spread out more over the entire range instead of close together like this.
Yeah, so at higher temperatures, it has a really big distribution. But keep in mind, it's the whole idea, if you have learned about integrals, the area under a curve, right? That the shaded area has to be equivalent because we're not adding or removing molecules, right? So the faster ones get more flat to mean that same amount of molecules, okay? All right, coming to our new graph, but using the same concept. This one is 2 different temperatures. So we have T1 in the solid line, or dashed line, T2 is the black line. This right here, E of A is the symbol for activation energy. Okay, so E of A is activation energy. The energy it takes to break the bonds, make the reaction go. What this graph shows us is that molecules at higher temperatures can overcome the activation energy more easily than at lower temperatures. So since T1 or T2 is greater than T1 in heat, more molecules can reach that activation energy, right? Because this one has this many molecules, that one only has that many. So the higher the temperature, here's kind of the pattern, the more molecules that can pass through. Or I'll just say hit the activation energy. So that's kind of the connection of how temperature helps reaction go faster. Is temperature gives them enough energy to reach that activation energy so they can actually be effective and not just bounce off each other. Okay, questions on that graph? Okay. Are you guys done with that? Oh, perfect. Okay. I'm going to go over this, and then they'll do a problem, and then I'll come to the next thing to do. If you want to stand there, you're welcome, or you can go back in the lab, and I'll come in there in a second. Okay, this right here is a reaction pathway diagram. Okay? What this does is it shows you the process of a reaction. Okay? The different parts of how we kind of read it is, first off, so the reaction pathway is like as it's progressing. So here's like the start. So this right here, this line represents the energy of the reactants. So how much energy do those reactants have? Because all molecules have stored energy inside of them, right? They have potential energy. Okay? The reaction proceeds by taking energy in. The hill is the activation energy. How much energy does it take to make it happen?
Does it matter if the A on it is like lowercase or uppercase? Or
E.
I don't know.
like, have to be like
I-
specifically like capitalized for both?
I've always seen it as capital E lower a. Because energy is always capital E, so that's always a for sure. But the A, I don't know. Is it capital on another one? I learned it as lower, so that's how I always write it. I guess the A doesn't matter,
Okay.
but the E does. Make that capital. Good observation though, Macy. I didn't even notice that it was different.
You said that the K mattered, and I was like, the same.
No, in chemistry, it's actually a legit question about capitalization. Like, does this matter? Because most of the time it does to some extent. So activation energy is from where we start to the top of the hill. Okay? Now, once again, I kind of visualize activation energy like a mini golf. Right? So if you have like those hills in mini golf, right? And if you're like me and you're real good, you hit the ball, and it goes up the hill, and then it comes back down the hill. You know what I'm talking about? You have to do it again, and then you get really angry, and then it goes really far. So activation energy is like that. If you don't give the molecules enough energy, they don't change. They just bounce off each other all day long. As soon as you give them that minimum energy, though, then they can start turning into product. Now, you can give them more than the minimum, and it will still go, right? The activation is just the minimum. Now, the top of our hill represents a point at which the molecules start to change. It is known as, so put it in this box up there, I'm going to write down here, but the top of the hill is known as the transition state, or it's also called the activated complex. Kind of just depends on who you talk to, what book you read. Your book uses both terms, but what that is, once again, is that's the point at which the bonds start to break and new bonds start to form, but they're not really reactants and they're not really products. Okay? So once we go down the hill, this is now our products and the energy of them. Now notice, in this reaction, we have energy in, going up, and we have energy out. Right? Both are in all reactions, but it's not normally totally equal. When the reactants have more energy, oh, wrong sign. When the reactants have more energy than the products, like in this problem, because the reactants are higher than the products are, what that means is that reaction releases energy. So this would be an example of a reaction that produces light, like a glow stick, or puts off heat and feels warm, or puts out electricity and can power a light bulb, right? Some form of energy, depending, on what it is. If it's reversed, if the reactants are lower than the products, that means the reaction is absorbing energy. And the energy is being taken in. This measurement right here is that energy change. So measuring from reactants to products tells you the overall energy change, which symbolically is represented by delta H. We'll have a unit where we learn all about delta H and how to calculate that. For now, just know that it represents energy or heat change. Questions on a reaction pathway graph, and what it shows us and what the different parts mean? Yeah,
So
Sam.
if there's not enough energy, does it still go to the bottom and it's just on the same level, or does it not go with that?
It all depends. As long as we have this much energy, then it can go. But if you don't have that much energy, then the molecules just move faster, but they don't ever change.
And what would the graph look like? Would it just be a straight line?
Yeah. Yeah, I mean, it could maybe, I guess, like go like this or something, but it would like never make its way to the end. So, good question. Other questions on that? Okay, with your table buddy, answer these two questions for me. Ready, set, go.
Actually, I would say if it would just be more like driving.
Okay, sorry. Okay, ready? Here's your sign. I'm going to point to the graph. If you're going to say that it's releasing energy, you're going to go like this. If it's absorbing energy, you're going to go like this.
Wait, that's gonna be
Spider.
Does that make sense? And then like freeze, right? Don't like keep doing it. Okay, ready? This one. Releases. Good. This one. Releases. This one. That's good. Okay, you're gonna smile, face, freeze. Okay, now show me on your fingers between graph 1, 2, or 3 which one is the slowest by your vote. Hold it under your chin. Hold it under your chin. Which graph is the slowest?
Oh.
Okay, everyone eyes up here, please. So the one that is the slowest, so when you gauge speed of reactions, as long as conditions are the same, that's what I wrote this was just to make sure you know conditions are the same. It's all about the activation energy. The higher the activation energy, the slower that reaction is going to be. So 2 is going to be the slowest reaction. So your order should be 2, 3, 1. So if you have 2, 3, 1, you can have a smiley face. Does that make sense though, now? If it didn't before? The higher the hill, the slower it will be. Yep, because it takes more energy for it to go. So, okay. All right, last thing for today, and then we're done. Okay, what about things that are not elementary? So when a process is not elementary, what that means is it takes more or multiple collisions for it to actually happen. These multi-step reactions can be written out as a mechanism. The mechanism shows you the process by which it's happening. For example, in this case, NO2 collides with NO2 and makes NO3 then NO. Then NO3 collides with a CO and makes NO2 and CO2. And you could have 2, 3, 4, 5, however many steps the mechanism takes. If you go and take organic chemistry, you'll learn about mechanisms that are like 20 steps long. Okay? Yeah. But first thing, the mechanism should add up to the overall reaction. Now, when you add up the overall reaction, so we're going to add these together, you do 2 things. You remove or cancel out substances that appear on both sides of the arrow.
Can we call those spectators?
We're going to have a different name for them. But it's kind of like how we cross out spectators, Macy. That's a good relationship. So if something appears on both sides, we're going to cancel it out. So starting there, and then I'll tell you the other thing we also want to look for. Does anyone see something that should cancel out here?
And the same step, like, can it be
It just has to be on opposite sides of the arrow.
Would it be NO?
No, no.
What the?
Whoa.
Here, skyward?
Sorry.
That was so weird. I've never had to just like jump away before. I don't even know where it went.
They're not the slideshows you are looking for.
Yeah, who did that? We do not have time for this.
Mr. Wyatt, I have a hacker.
Oh, that's what
2 sides.
Oh, there it is. Okay. Now I lost my mouse. Where is it? Okay.
Now we're back to the beginning.
Oh, okay. Okay, so what were we saying cancels?
NO3.
NO3. All right, so there's an NO3 on this side and an NO3 on that side.
Oh, yeah.
They cancel out.
Okay, so NO2.
Oh, then NO2 also.
So one NO2 can cancel, right? Because there's one over here and one there. There's another NO2, but that doesn't cancel because
There's not another.
there's not another one to cancel. Okay? Does that make sense? Now the other thing you look for is when you add them together, you are also going to combine like substances together if they're on the same side. So if it's the same substance on the same side, you can combine it and say you have two of them. So combine like substances on the same side of the arrow.
So what can you do about
If, hypothetically, Calvin, this one didn't cancel, then we would have combined them and wrote two NO2s. But since one of them canceled, now there's nothing to combine it with. So my overall reaction is going to look like this. NO2 plus CO changing into NO and CO2. Okay? So this is the overall reaction. This right here, everyone, this is what you've been seeing all year. You have been seeing overall reactions. But there's often a lot that goes behind the scenes of an overall. It should already be balanced if you add it up correctly.
But like, there's like two carbon oh, never mind. I'm just.
No, but that's a great question, Sam. If you add correctly, the overall should be balanced from the mechanisms. Now, let's label this. So these are the reactants of the overall.
And these background reactions would happen more likely than the overall reaction. Both the overall could happen. It's just they probably have a higher actuation point than these background reactions.
It's that in order for this to happen, these both happen first, actually.
Okay.
Does that make sense? So it's like, we look at it like this, but really it does this and then it does that. And then that's how we get this.
Okay.
Now let's talk about the things we canceled. We have two different types of things we've canceled. Okay, let's start with the NO3. Okay, so where does the NO3 first show up in this process? The end of step 1. So NO3 was created, but then what happens to it? It gets used up. Okay, so we created it, or the reaction created it, but then it used it. Someone last period said, oh, an intermediate is like a cookie. I make it and then I eat it. Okay?
Yeah.
So that's what we call it. NO3 is what is known as an intermediate. An intermediate is made in one step, used up in the other, so you actually never see it in the end. But it is stable enough to be detected through lab processes as it's proceeding. Yeah, but if you just let it go to the end, it won't ever have been there.
Did you try and get like an excess amount of NO3?
Yeah, so you can like some reactions you could technically stop after one step if you wanted and see the intermediate and then have it continue onward. Yeah. Yeah, Sam?
Why on step 1 isn't the reactant written as NO2?
It could have been. I wrote it that way just to help you see the canceling.
Oh, okay.
But it totally could have been written that way and it'd be the same thing. So, yeah, Norm.
So to know the intermediate molecules, is it just determined experimentally, or can we figure it out given an overall equation?
So, given a mechanism that someone else determined experimentally, we can see it. But from just an overall to go to here, that's the experimental part once again. So this is a case where there's experimental data that goes into getting there. Okay, last thing, write this down really quick. So NO2 is not an intermediate. What's different about NO2 versus NO3?
It still shows up after.
We started with it and we end with it. That's a catalyst. Catalyst we put in and they come back out. Okay? All right. I got one small homework assignment for you. It's super, super fast.